Hi guys, in this video we are going to continue on the organic chemistry on the subtopic of isomerism, and let's just do a quick review. In our previous video we talked about different types of isomerism, and so first of all, isomerisms are molecules with the same molecular formula, so they have the same number of atoms, but the atoms are bonded in different ways, or the atoms or the groups of atoms are arranged differently in the three-dimensional space. Okay? Now, if the isomers have different structures, then they belong to the structural isomerism. Okay? If they have the same structure, however, the atoms or groups of atoms are arranged differently in the three-dimensional space, then we will call those stereoisomerism. Okay? Now, for structural isomerism, we further divided into three types. So we did talk about it last time. If you want to recap this part, you can revisit our previous video. Now, today we will focus on the stereoisomerism, and last time we also discussed the cis-trans isomerism, where we have a double bond or even a small ring, a cyclic compound with a small ring. Again, the bond rotation is restricted, meaning that if the two groups, for example, over here, if you use this as an example, if the two bulky groups or the large groups are located at one side, then their position will be confined, meaning that these bulky groups cannot freely interchange into this configuration. Once they are fixed like this, they are fixed forever, unless you break the bond and reform it. But that would be a chemical reaction. Okay, so the double bond does not allow bond rotation, and therefore resulting in the existence of cis-trans isomers. Okay, now you may notice they have exactly the same structure, right? All the atoms are bonded in the same way. They are bonded to the same atom with the same kind of bonds, right? But the difference is how we arrange the bulky groups, the large groups. So this is what we're trying to say, the atoms or the groups of atoms are arranged differently in the three-dimensional space, and hence the stereoisomerism. Okay? Now, so this is not too difficult to understand, right? The two groups are on the same side versus the two groups on opposite side, right? Now, today, we will talk about the enantiomerism, which is a little bit abstract, require you to utilize some of your three-dimensional thinking to see how you guys fare in this part. Okay, so first of all, again, I want to introduce the Chinese version of this one. The Chinese one is called, here, okay, again, the Chinese name gives us a more authentic idea. So this part, we are trying to talk about like a mirror, like a mirror. Because when you look into a mirror, you see another image of yourself, right? So it's like the opposite image of yours, okay? So this is what the Chinese version implies, okay? So it has to do with a mirror and the image that is formed when you look into a mirror. Okay? Now, we will break it down for you one by one, and you will see how this one is related to the mirror and the image. Okay? Now, here, let's just say we have a organic compound, a simple organic compound, 1,1-dichloroethane. Okay? So if you look at this carbon, this particular carbon, so this carbon should adopt a tetrahedral structure, okay? Because it has 4 bond pairs and no lone pair, so it should adopt a tetrahedral shape. So, you see there are 4 atoms or 4 groups of atoms attached to this carbon, and you see if there are 2 atoms or 2 groups of atoms that are the same, then they will exhibit an internal plane of symmetry. Now, what do you mean by internal plane of symmetry? Now, this diagram hopefully can give you a more authentic idea. So, this one is essentially this one, but I put it in a more 3-dimensional ball and stick diagram. So you notice, if we try to look for a plane of symmetry, you can follow this pink layer bisecting the CH3 and the carbon bond. And you notice this side and the side on the opposite side of the pink sheet, you see they actually are symmetrical. Okay, so this side and the opposite side of the pink sheet, they are actually symmetrical. And you see this plane of symmetry is bisecting the molecule itself. So that's why we call it internal plane of symmetry. Okay? Now, what is it important about this internal plane of symmetry? Now, if a molecule exhibits an internal plane of symmetry, then we will say the molecule is symmetrical. Symmetrical. And why is this symmetrical structure? Why is it important? Now, when it is symmetrical, okay, when it is symmetrical, or later on we will use the word achiral, but I will talk about it later. These two is actually having very similar meaning, but at least you know symmetrical, right? Okay. Now, if it is symmetrical, then you look at this one. Like I said, the whole enantiomerism is talking about mirror and the mirror image. So what we're trying to do is we try to put a mirror, okay, in front of this molecule. Then from the mirror, it should give you a mirror image, which will be like this. Now you notice a mirror image is not exactly the same as the real object. Actually, it's kind of inverted. Okay, if you want to try very easily, you can get yourself a mirror, or you can actually use an actual mirror, which is your calculator or your mobile phone, but in the exam you can't use a mobile phone. And what you're trying to do is, you see this is the original image. Then actually your screen can serve as a mirror. Then you just look into the screen. Now it may not be that clear in the video, but you do see an image, right, over here. That would be an image. Okay, and this image, if you look at the shape, it's actually different from the original object. And this one, if you memorize this, you see, boom, this is essentially this one. Okay, see this one, the image here, the image here is the same as this one. So this is what we call the mirror image. So now, if you are not sure about how the mirror image looks like, get yourself a mirror and find it yourself. Okay? Now, you notice this mirror image is formed when you rotate this CC bond 180, then you will form this one. Now, let me show you. I built this model early on. This one is actually the same as this one. So try to show you. And remember, the dashes means pointing out of the paper. The wedges means this atom is pointing out of the paper. Now it's pointing towards you. Okay, and this dashes means that the atom is pointing into the paper. So in this case, pointing away from you. So this one corresponds to this. Okay, now this will be the CC bond, and now let's rotate it 180 degrees and see what happened. Okay. Okay, so now it has rotated 180. So you now notice this one will be the same as this. See again the chlorine pointing out of the paper, and then this chlorine pointing into the paper. Okay, the hydrogen will pointing towards this one. Now I have made another one. Let's just kind of rotate it back another 180, so it goes back to this one. Now I have also prepared the mirror image. Okay, mirror image. Now you notice, so I kind of aligned it according to my notes. Okay, so you notice this one is the mirror image of this, or you can do it another way around. This one is the mirror image of this. Okay, now what I wanted to show you is, my question is, are these two molecules able to perfectly overlap with one another? Okay, I repeat, can these two structures overlap on one another perfectly? So what do you mean by overlap on each other perfectly? That means when I overlap the two molecules together, if it really overlaps perfectly, you should only see one molecule instead of two. Okay, do you get it? Let's just say, for example, if I have something that is perfectly symmetrical, and when you overlap them together, let's just say, obviously, okay, I have these two objects, and these two objects are perfectly symmetrical, right? So when I overlap them, you see, supposedly, you should only see the purple one. You should not see any white one. Okay, so this one is what we call overlap on one another perfectly. Okay, you can't see the white. Okay, it's not magic trick. I just put it on top. Okay, so let's see if it works. Now you see, going back to this situation where we have the 1,2,1,1 dichloroethane and its mirror image. Now watch very carefully. If I just simply rotate this one like this and then put it on top, boom. Now I think you can also see it from the video. Now you see, you should not be able to see the molecules closer to the paper underneath, right? So supposingly, you should only see one molecule instead of two, all right? So this is what we call overlap perfectly, or in chemistry, we will use the word superimposable. Superimposable here, okay? So superimposable means it can overlap perfectly. So if they align it this way, and let's just say you are standing here, okay, observing the two molecules, you should only be able to see the molecule closer to your eye. You should not be able to see this one because that would be completely blocked by this one. So this one is called superimposable. So now you notice one thing. When the two molecules are symmetrical, then they will be superimposable. That will be superimposable. And therefore, these two are in fact the same molecule. The same molecule. So when they are the same molecule, they do not exhibit enantiomerism. Okay, they do not exhibit enantiomerism. Okay, so let me quickly put down a remark here, a quick summary, a conclusion. So when two atoms are the same, okay, just now here, two atoms are the same, right here and here, okay, then it does not have, okay, the internal plane of symmetry. Okay, so it does not, it does have, make a mistake, it does have an internal plane of symmetry, just like this, okay? That means they are symmetrical, or we can use the word atidal, okay? And therefore, the original and mirror image are superimposable, okay, are superimposable, which is referring to this. The original molecules and the mirror image are superimposable. They can be overlapped perfectly on one another, and the conclusion would be they are the same molecule. Okay, So if they are the same molecule, they do not exhibit enantiomerism. Okay, so basically these are what we have discussed. Okay, if you kind of connect all the concepts that we have talked about. Okay, so that would be the idea. Now, what if we had another situation here? So you look at this one. This time, what we're trying to do is to replace one of the chlorine atoms by a bromine atoms. You see here, this one, 2 Cl atoms. Now I just replace one of them by the Br. So let me show you with the model. Okay. So what we are trying to do is we take away the chlorine, and now we stuck in the bromine. Okay. Okay, so now this one will be this one, okay? And just do the same thing with another molecule. Okay, so now, okay, like this. So I try to align it the same way as the textbook. So now we have this one, okay? And as it rotates 180, like this, okay, now it becomes this one, okay? And that would be here, okay? So these are the original one and the mirror image. Now, I try to do the same thing to see if they can overlap one another perfectly. So I will do the same thing as before. Try to align it like this, or maybe if I follow this one, we have this one and this one. Okay, so now I'll align it like this. Okay, maybe I'll hold on to the hydrogen atom. Now, do you think they are completely superimposable to one another? Okay. Now you may notice let's see. Okay, I should put it this way. It's quite difficult to hold it. Okay, I try to align it this way. That would be better for you to see it. If you put it this way, then as you look into the compound, can they completely superimpose? Or maybe I'll put it this way. This would be better. Yeah, I try to put it this way. That would be easier to see it. Okay. Now you see, can the one at the top completely block the molecule at the back? You see, not really, because you see here. Now this one can, this hydrogen atom can completely block this one at the bottom, same as the carbon. But this chlorine atom, can it completely overlap with the bromine atom at the back? No, you still see the bromine here, right? Similar idea now, but this one, the bromine atom is bigger than the chlorine, that's why it can block it. But at least this part, you see, they are not perfectly overlapping one another. So these two, we say that they are not superimposable, So if you look at here, they are not superimposable. Okay, when you look at it from here, then you should see that this chlorine atom is unable to block this bromine atom. When you look at it, you should see the bromine atom, part of it, not being blocked away by the chlorine atom. So anyway, the idea is to show you that when you have a carbon connected to 4 different atoms or 4 different groups of atoms, then the 2 images will be not superimposable. So you see here, if we have asymmetrical molecules, because this one will be asymmetrical, then the molecule is not superimposable with one another. So in this case, the original molecule and the mirror image are two different molecules. And these two isomers will be called enantiomers. So now you understand what is enantiomerism. Enantiomerism is when we have asymmetrical molecules where the original and the mirror image is not superimposable, meaning that these two are two different molecules, and we will talk about this, we will describe these two are enantiomers. Okay? So that's the idea. Now, once you understand enantiomerism arises from asymmetrical compound, then we can move on to talk more about the terms that we commonly use. So for enantiomerism, like I said, it occurs when the two isomers that are mirror image of one another, however, they are not superimposable. Excuse me. Right, excuse me, but don't worry, I'm fine, just allergy. Okay? Now, here, so now we're trying to be more focused on organic chemistry, how enantiomerism is related to the structure of an organic compound. So here, we say that when we have a compound where we can see one carbon connected to four different atoms or groups of atoms. You see 1, 2, 3, 4. We have 4 different atoms or groups of atoms. Then this carbon, we say that it is a chiral center. Chiral center. Now, chiral center, or here, chirality in Chinese, okay, it means this one. That means a property of hand. Now, what do you mean by property of hand? Now, because if you notice your hand over here, actually, your hand is asymmetrical. Both of your hands are asymmetrical. So that means they are not superimposable from one another. So you see, when I try to overlap one another, you see, they are not completely overlapping one another. You see, here, my hand closer to your screen, okay, my pinky is unable to block away my thumb from the hand that is away from you, okay? So that's why you will still see my thumb, okay, of my hand that is away from you. Anyway, so the idea is, just like our hand, they are asymmetrical, therefore they are not superimposable, okay? So that means, okay, chirality or chiral actually means asymmetrical, okay? So that's why in here, when we have a carbon with 4 different atoms or groups of atoms, then they are asymmetrical, or we can describe it as chiral. And because this chirality is coming from this carbon, we call this carbon a chiral center, or a chiral carbon, okay? So starting from now, whenever you see 4 different atoms or groups of atoms connected to a carbon atom, then this carbon atom will be the chiral carbon or chiral center. Okay? And usually we will indicate the chiral center using an asterisk here. Okay? And usually past paper will ask you to use the same symbol to represent the chiral center. Okay? So just like this. Okay? Now, for mirror image, you need to know how to draw the mirror image. So use a dotted line to represent the mirror, and you just draw the corresponding mirror image. Try to practice how to draw this one, because sometimes the past paper may ask you to draw both image. Now, a tricky way of doing this is to actually use a mirror. So when you draw the first original image, and you put the mirror here, and you will see the mirror image, right? You see the mirror image. Not very clear from the screen, but I do see it from my calculator. And what you're going to do is just copy this one, then that would be the answer. Okay? But of course, my suggestion is you know how to draw it without a calculator, without a mirror. But well, this is a trick which you can do it in the exam because the calculator is available. Okay? Now, so that's the idea. Now down here we have two more terms that you need to know. By the way, one more thing. Like I said, here, chiral means asymmetrical. Okay? Because just like our hand, okay, our hand is asymmetrical. So what about if we have a symmetrical molecule? Then we will say it as achiral. Achiral, that means not resemble to our hand, okay? Alright, so try to get used to these two terms. Usually in chemistry, we will use these two terms more often than these two. You know, it's kind of the opposite of one another, so make sure you can sort this out. Now here, optical isomer and reciprocal mixture. So here, for enantiomer, you may notice they have exactly the same structure, and unlike cis-trans isomer, cis-trans isomer, the different distribution of bulky groups may result in two different shapes, and therefore leading to slightly different in physical properties, right? But for enantiomer, their physical property and chemical property is very similar. As a matter of fact, the chemical property in DSE level is the same. Okay, in A level they are not the same. For physical property, all the physical properties are the same except for one, which is the optical activity. Optical activity. So, what do you mean by optical activity or optical properties? Optical means light. That means the two enantiomer may behave differently or may respond differently in terms of the light. Now here, we say that the only distinguishable physical parameter, now you can't use boiling point, melting point, density, blah, blah, blah. It doesn't work, they are all the same. But the only physical parameter where allow us to distinguish between two enantiomers is their interaction with plane polarized light. Okay? Now, let's look at this diagram. So this one is to show you the key components in a device called polarimeter. Okay, a polarimeter. Now, polarimeter is used to distinguish between two enantiomers based on their interaction with plane polarized light. Now, I understand there are a couple of terms new to you and quite physics, to be honest. These are all physics stuff. So I try to break it down for you as simple as possible. Now, light, okay, coming from LED, coming from sunlight, we say those lights are not plane polarized. That means, think about light as wave with all the direction, with 360 direction. From 0 degree to 360 degree, we have wave from all the direction. So they are not polarized. If we can select one particular direction of wavelength, one direction of wave, then that light will be described as polarized or plane polarized. Okay? So what we try to do here is, think about it, we have a lamp here, a light bulb, a sodium lamp, so it will be emitting unpolarized light, meaning that light with wave of all the directions. And we put it into a dark box and we poke a hole here, so we have a linear unpolarized light with all the direction of wave. Then we will use something called polarizer. or in physics you may call it a polarizer. Okay? And what a polarizer does is that it has some slit that will only allow one particular direction of wave to pass through. And other wave with the direction not corresponding to the slit will be blocked away by the polarizer. So here, with all the direction entering the polarizer, only one particular direction of wave are able to pass through. So here, this one, we will say it as a plane polarized light. Okay? Plane polarized light. This one is unpolarized. Okay? Unpolarized. Now, so with this plane polarized light, we will direct it into our sample. Our sample, we call it a polarizing tube or a sample tube. This is the place where we put in our sample. Okay, we put in our sample. And if our sample is enantiomers, they are able to rotate. They are able to rotate a plane polarized light. So as they rotate the plane polarized light, then obviously the direction of the wave will also be rotated, will be changed. So now, when we use another polarizer, now actually this one is called an analyzer, but this one is the same as this one. Actually, these two are two identical pieces of polaroid, meaning that they only allow certain direction of wave to pass through. Now think about it. So if you have this one, okay, you put it here. If the direction, if the slit is still vertical, then these lights are unable to pass through. So if you use this one and put it here, you can't see any light coming through from the polaroid. Then if you actually do it, you won't see any light. It's all dark. Okay? So what you're trying to do is you rotate the polaroid. You rotate this this little device so that to the point where you start to see light. And that degree of rotation would be the same as the rotation done by our enantiomer. So this angle of rotation, you can record it, okay? And you later on can use another sample, probably the mirror image of the sample, okay? Then what you will expect to see is it will perform a rotation of the same degree but to a different direction. So here, let's just say this is the original molecule, so one of the two enantiomers. If you put another enantiomers inside, you will expect to see the rotation not in a clockwise direction, perhaps in an anti-clockwise direction. So then, imagine you have another tube here. Imagine you have another tube here. So this time, the plane polarized light will rotate it this way. We'll rotate it this way. So probably the one coming out will rotate it in another way around. So this time you may need to use another analyzer with the slit aligning in this direction rather than this direction. Then you are able to register the angle of rotation of an anti-clockwise direction. Okay, now this one is clockwise, right? But you will register an anti-clockwise angle of rotation. And one more thing that is interesting is that these two angles are the same. The only difference is the direction of rotation. Okay, so basically scientists or us, if we try to distinguish between two enantiomers, we will perform experiments using two different samples using the polarimeter. And what we try to do is we try to look at the angle of rotation. The two enantiomers will rotate the plane polarized light to the same degree, but different direction. One clockwise, one anti-clockwise. So judging from the direction of which the plane polarized light is rotated, then we are able to deduce which enantiomer it is. So that is the idea. I understand, quite complicated, very physics. So try to understand, I try to explain it as simple as possible in terms of chemistry. Okay? So that's the idea. Now let's just quickly look at some keywords, like look at how in chemistry, how we describe polarimeter, how does it work. So here, excuse me. Okay, let's have a look. We say that enantiomers are optical isomers, like I said, because they have different optical behavior. Now, for the same concentration and same temperature, enantiomers will rotate, okay, rotate a plane polarized light to the same degree, but different direction, okay? So that one will rotate in a clockwise direction while another one will rotate in an anti-clockwise direction. So this is how we distinguish between the two enantiomers, okay? And this, okay, I would say this one, very important. This one, please memorize this. Please memorize this paragraph, okay? Because usually the question, if they ask you how you can distinguish between the two enantiomers, this is what you're trying to answer, okay? All right, now down here, finally we have the last term. We call it racemic mixture. Racemic mixture. Okay, racemic mixture. Again, I like to introduce the Chinese version of these terms because I feel like the Chinese version is very much self-explanatory. Make it quite easy to understand what is going on. So here, you see, we try to cancel out the rotation, right? Cancel out the rotation. It's a mixture that is able to cancel out the rotation, all right? So what is going on here is basically we have a mixture of exact equal proportion of the two enantiomers, okay? So think about it. One enantiomer will rotate in a clockwise direction, another one will rotate in an anti-clockwise direction. So if we have exactly 50-50 of the two enantiomers, so the rotation will be exactly cancel out one another. So as a result, the two enantiomer, the rotation of the lights cancel out one another, and therefore the racemic mixture will show no optical activity. So no rotation of light, no rotation of light. Meaning that if you have a racemic mixture loaded into the polarizing tube here, then after we select a particular direction of wave, then here, the analyzer, you don't have to rotate anything. You just keep it as the same orientation as the polarizer, and you will see the lights coming out. Then that means there are no rotation of plane polarized light, meaning that the sample shows no optical activity. Okay, so this one is a very special case. Bear in mind. Now, if we do not have exactly 50-50, let's just say we have a 40-60%, 40 versus 60, then still we will have a net rotation. Okay, so racemic mixture emphasize that there must be exact equal proportion. Okay, so that would be the meaning of all these terms. Okay, now we have some practice question. So again, pause the video. Let's focus on the first one first. Okay, what we are trying to do is to mark down all the chiral centers. Okay, I think you should be able to manage the first four. The fifth and the sixth one are quite challenging, so you may try to work it out. Pause the video, as always. Okay, so let's check. So for chlorobutane, the chiral center is here. For valine, the chiral center would be here. Okay. For ibuprofen, the chiral center should be over here. For straight chain glucose, there are a couple of chiral centers, including this one, this one, this one, and this one. Okay. The key is one carbon connected to 4 different things. So you can look at this one. If you look at this chiral carbon, you can think about this carbon connected to a hydroxyl group, hydrogen, an aldehyde group, and a whole chunk of things that is left. So obviously, these 4 are 4 different groups. Okay. Now, let's look at cholesterol. Could be more complicated. So that includes here, here, and then as well as this one, this one, this one, this one, this one, this one, and that should do it. 1, 2, 3, 4, 5, 6, 7, 8. Should have 8 chiral center. Okay. Anything left? I think that is okay. Yep. So what about penicillin G here? So the chiral carbon would be here, here, and here. Okay. So these are the 3 chiral carbon. Okay. Right. Now down here. So draw both enantiomer for each of 2 chlorobutane and valine. So this is to practice drawing the mirror images. These 2 are based on the 2 molecules here, so you got the structure already. Now, whenever you have to show the mirror image, you must use 3-dimensional drawings. So meaning that you must have to locate the chiral carbon and then draw the tetrahedral shape and then put in the things that is attached to the chiral center, chiral carbon. Okay. So for 2-chlorobutane, we first draw the carbon here, the chiral center, and we can first draw out the tetrahedral framework. Similar idea for the mirror image, and then we plug in the things. So we have hydrogen. It doesn't matter where you put it. So for me, I will put the hydrogen here, the chlorine here. As long as they match, it doesn't matter. The ethyl group here. And lastly, an ethyl group here. So that's the idea. Okay? You can always double check by using a calculator, put it here, and check the mirror image to see if that is what you want. Okay? Alright? So similar things goes for valine. Again, we draw the tetrahedral framework, and then we plug in all the items. Okay, so for valine, so we have a hydrogen atom, an isopropyl group, amino group, and carboxyl group. It doesn't matter which way you put them. Again, you can have H here, you can have COOH here, COOH here, H, NH2, NH2, and then the isopropyl group, CH, CH3, 2, CH, CH3, 2, like this, okay? Or you can draw out the isopropyl group, it doesn't matter. Now, so this is how you show the enantiomers. Okay, Another question on the right hand side, a long question focusing on the enantiomerism and isomerism as a whole. So here, there are several structural isomers with the molecular formula C5H11Cl. One of the structural isomers has a chiral carbon and exhibit enantiomerism. Okay, so first of all, what do you mean by chiral carbon? So basically, a carbon bonded to 4 different atoms or groups of atoms. Okay? A carbon bonded to 4 different atoms or groups of atoms. Okay? Now, draw the structure of isomer that has a chiral carbon and its enantiomer. So for this one, you need to figure out an isomer that fulfills this criteria. So you can first use the expanded structural formula to figure out. So it will probably be this one. Not this one, sorry. Let me think. Probably this one. And then we have the propyl group that follows. Okay, so that one, you see this one will be the chiral center, methyl group, propyl group, choral group, and hydrogen atom. So this one will be the chiral center. Okay, so if you know this one, then we can draw it in the form of tetrahedral framework shape. So C like this. Then I can choose to put down the chlorine here, the hydrogen here, the methyl group here, and the CH2, CH2, CH3, and the CH2, CH2, CH3. Okay, that's the idea. And then explain the boiling point between the 2 enantiomers. Now the difference will be they have the same boiling point. Okay. So now why do they have the same boiling point? It's because they have the same structure and molecular size. Therefore, the strength of van der Waals force among molecules are the same. So again, whenever they talk about the physical property like boiling point, melting point, you need to talk about the strength of intermolecular force, in this case the van der Waals force, because they have the same structure and the same molecular size. So their strength of van der Waals force has to be the same. So this is how you explain it this way. Now probably a new type of question, because usually they ask you why they have a difference, but they rarely ask you why do they have the same boiling point, or why do they have the same melting point. So, but again, whenever we talk about physical property, it all boils down to the intermolecular force. Okay. So this is the 2 key points you need to mention. Excuse me. Okay, so the 2 enantiomers can be distinguished by a polarimeter. Describe briefly how this device can distinguish the 2 enantiomers. So this one is actually based on the notes, the one that I have highlighted. So you should put down the 2 enantiomers, okay, rotate the plane polarized light. Now you must use the word plane polarized lights. These are the key words, okay? To the same degree, but different direction. Okay? So there are a lot of keywords, and make sure you don't miss them. So rotate plane polarized light, I think that would be 1 mark. Same degree, same angle, but different direction. That would be the 2nd mark. So make sure you include all these keywords. Okay, and the last one is to evaluate a statement. There is no observable change when a mixture of 2 enantiomers are examined by polarimeter. So this one has to do with the racemic mixture, but like I said, a racemic mixture requires exactly 50-50 portion. Simply a mixture does not guarantee having a 50-50 proportion. So that's why this statement is not necessarily true. So when you have to evaluate this statement, you may have to say that, okay, only when the 2 enantiomers are of exactly same amount, then the rotation of plane polarized light will be cancelled out completely. Okay? If the amount is not the same, then okay, the mixture will still rotate the plane polarized light, still have net rotation of the plane polarized light, and thus showing or exhibiting optical activity. Okay, so I make a little bit more comment because question like this, you try to give as comprehensive as possible. So you try to describe the 2 situations. And the first situation is when they are having exactly the same amount, then the rotation of the plane polarized light cancel out completely. Then that would be no observable change. If the amount is not the same, then they will still have a net rotation of plane polarized light, and therefore giving you an observation or showing an optical activity. Okay? So I think the key is you mentioned about the 2 situations, the 2 conditions. Okay? So that's the idea. Now the rest of them will be a multiple choice question, and then we will enter the functional group chemistry. Now, so here, actually this is the key part of organic chemistry. We try to focus on the chemical reaction of these molecular series. Some of them we have already learned. For example, alkane and alkene. So I will not spend too much time talking about these. Okay, so these are all the a condensed version of the fossil fuels notes. Okay, talking about all the reactions involved. So for details, you can revisit the notes from the fossil fuels and carbon compounds, and or revisit some of the video that I have talked about. So I'm not going to repeat myself here with the alkane as well as the alkene. But for alkene, there are some extra things that you have to pay attention to. Okay, so which is here. Okay, this one is what we call Markovnikov's rule. Markovnikov's rule. So here, let's just say we have an addition reaction of hydrogen bromide to propene. Okay, now you see it gives rises to 2 possible products. Now, let's just look at, before we look at this example, let's just look at the addition reaction with ethene. Okay, now let's just say we have ethene Now, with the CC double bond, it is capable of undergoing addition reaction with hydrogen bromide as well. Now, if you react with HBr, then the question is, okay, where will the Br be added into? Will it be added to the carbon on the left, or will it be added to the carbon on the right? Now, in this situation, you may realize that it actually doesn't matter, right? It doesn't matter, right? It doesn't matter where the Br is added to the carbon on the left, or whether it is added to the carbon on the right. Because you realize that these two are the same compound. It's the same molecule, right? So, actually, for ethene, it does not have any problem as to which product is being formed. Now, you may also extend this concept to all the alkene that is symmetrical. Now, for example, this also true for butylene, right? It's also true for example, okay, cyclohexene, right? Now, all these symmetrical alkene, we don't have to consider whether the bromine atom is added to the left or added to the right. We don't have to care because it will all be the same. However, when we come across to something what we call asymmetrical alkene, okay, such as propene, then we will have this problem as to where the bromine atom should be added. Now, in this case, here the bromine atom is added to the second carbon, and here the bromine atom is added to the first carbon, resulting in two position isomer. So the question is, will it be formed in a 50-50 proportion, or would that be a major and minor product? Would that be like, for example, 80% of this and then 20% of this? Or would it be the other way around? Is it going to be 20% of this and 80% of this? Or should we rather have it 50-50? So this is our consideration. Now, to predict which one being the major product, we need to follow the Markovnikov's rule. Okay? So Markovnikov, this guy, have proposed a rule allowing us to predict which position isomer would be the major product. So this Markovnikov rule, let's see what he says. Now he said that when we have an addition of hydrogen halide, HBr, okay, to an unsymmetrical alkene, that means asymmetrical, for example, propene, the hydrogen will be added to the carbon with fewer alkyl substituents. So, what do you mean by fewer alkyl substituents? So here, let me circle with a red ball pen. Now, let's look at these two, okay? Now, let's look at the carbon of which the hydrogen is attached to. Now, in this case, if you focus on this carbon, this carbon, how many alkyl substituents does it attach to? So there are altogether 1 alkyl substituent connected to this hydrogen atom, right? The rest of them are 2 hydrogen atoms, okay? So when this hydrogen is added to this carbon is attached to 1 alkyl substituent. Now, if you look at this scenario, this situation, this carbon is attached to 1 and perhaps 2 alkyl substituents, okay? So the addition reaction forming this product, we must have the hydrogen atom connected to a carbon with 2 alkyl substituents. So the question is, let's go back to our Markovnikov's rule. It says that the hydrogen will prefer a carbon with fewer alkyl substituents. So do you think the hydrogen would prefer this carbon, or would the hydrogen prefer this carbon? So according to Markovnikov rule, it prefers this one because it has only one alkyl substituent attached to the carbon, but here it has two. So it turns out that this one would be the major product. The major product. And this one will be the minor product. So maybe it is 80% and this is 20%. Maybe I just make it up. Okay? So you see, there is a preference based on the structure of the alkene as to where the hydrogen will be connected to. Okay? So you see, therefore, let me make it bigger. So we said that the 2-bromopropane would therefore be the major product, whereas the 1-bromopropane will be the minor product. Okay? Now, so that's the idea. Now, first of all, you notice, for Markovnikov rules, it does not give us any explanation. It is just a rule that allows us to predict which one is the major product. It is not an explanation. There is no explanation at all, right? For the detailed explanation, it is out of the HKDSC scope before it was in A level, but I would just want to briefly talk about why this is the case. The idea is, think about it, when you open up the double bond, then we will plug in the atoms. In fact, they will first plug in the hydrogen atom, then it will plug in the bromine atom. So it turns out that when they insert the hydrogen atom, then one of the carbons will bearing a positive charge. Now, when the hydrogen atom is added to the first carbon, then the positive charge would appear in the second carbon because it has only 3 bonds. Similarly, if the hydrogen atom is connected to the second carbon, then the first carbon will be bearing a positive charge. Now, according to your common chemical knowledge, you should know that for carbon, it does not usually exhibit positive charge. As a matter of fact, carbon bearing a positive charge is highly unstable. Okay? So these two, we have a name. We call them carbocation. Carbocation. Okay? And it turns out that these two are both very unstable. However, even they are very unstable, there is still a more stable, unstable carbocation. Okay? A more stable, unstable carbocation. It turns out that this one, a secondary carbocation. A secondary means that this carbocation is surrounded by 2 alkyl groups. Okay? And this one primary means that the carbocation is connected to 1 alkyl groups. It turns out that the one that is sandwiched or kind of connected to more alkyl groups will appear more stable. Okay? And the reason is due to something called positive inductive effect. And positive inductive effect basically means the alkyl groups are able to push electrons towards the carbon positive center. And when the electrons are pushed to the carbon positive center, it helps to minimize the positive charge, and therefore stabilizing the carbocation. Therefore, with more alkyl groups pushing the electron towards the carbon positive center, this allows the carbocation to be more stable, and therefore forming the secondary carbocation is more favorable. And this is the reason why this one is more preferable. Okay? And this is the reason why the hydrogen atom will be added to the less substituted carbon. Okay? So later on, the bromine atom will inevitably added to this carbon, forming the major product. Okay? So that would be the explanation. All right? So that's the idea. Okay? So this is something new. Okay, so regarding the Markovnikov rule, there are some practice questions. Now, because this is something new, not in the fossil fuels and carbon compound topic, so need you to be able to apply the Markovnikov rule. Remember, Markovnikov rule, hydrogen added to the less substituted carbon. Okay. In fact, you may also think about it in another perspective. So if the hydrogen atom is added to the less substituted carbon, in other words, the halogen will be added to the more substituted carbon. You get it? Let me flip it and let me show you. So like I said, this one is the major product, right? This one is the major product. And this major product is having the hydrogen atom added to the less substituted carbon. And when the hydrogen atom is added to the less substituted carbon, the halogen must be added to the more substituted carbon, right? So that's why you can think about it either with the hydrogen atom added to the less substituted carbon or the bromine added to the more substituted carbon, okay? So that's the idea. Okay, so practice question. Let's do it by yourself. Pause the video, try the question. Okay, so let me show you the answer. So here, the chlorine atom, actually in this case, because this is a symmetrical alkene, so it doesn't matter. It only forms one single product. Okay. Okay. So it does not have to show major and minor. Okay. Now for the second one, this time, this is also symmetrical, right? So it should not give you any other product. Okay. But here you see this is AQ. So there is a chance where OH could be added into it. So this one, I think both will be acceptable because it's concentrated. So I think I will stick with an addition reaction with the HBr rather than forming a bromo alcohol. Okay. Well, actually, I'm not sure. Anyway, now here it starts to make a difference because this one is an asymmetrical alkene. So it should give us two different products. It should give us, for example, it should give us this one and this one. Okay? So depending on where you put the H or where you put the Br, and which one is the major product. So this one is the major product. Major. Okay? All right? Now, if you cannot really follow, you can think about the HBr, the red. Let's just say this is red in color. So when you add into this double bond, so in this case, if you think about the Br is added in here, the H is added in here. In this case, the Br is added to here, and then think about one of the H's, okay, is added here, okay, so across the double bond. Now you notice, if you follow the Markovnikov rule, in this case, the H is attached to a carbon with 3 alkyl substituent. Whereas in this situation, the hydrogen atom is added to the carbon with just 1 alkyl substituent. So this one is, of course, more preferable according to Markovnikov rule. So this one is the major product. Now here, co-caramidophyl alkaline, so this one will give you a dialcohol. So it does not give you any major or minor products. Okay, just like this. And this one, HI dissolved in Water-Seal 244. Now, Water-Seal 244 is a very common organic solvent. You need to know this because in DSE it was asked before. Okay, you need to know this one is an organic solvent. Okay, now so here the decision would be whether the iodine should be attached to here or here. So similar idea. We will like to have our iodine attached to a more substituted carbon, or the hydrogen attached to a less substituted carbon. So we can have this one. And we can have this here. Okay, so which one is the major product? Of course, this one will be the major product. Okay, because you see, the difference is that this one has 3 acal substituents, and this one has only 2 acal substituents. So the hydrogen adding to this one is more preferable according to Markovnikov rule. So the iodine added to this one is the major product. So this one should be the major product. Okay. Think about it. H. One is here, another one is here. Okay. So again, like I said, you can look at the position of halogen, or you look at the position of hydrogen. Okay. So down here we have another tricky question. So here, butyl-1,3-diene, okay, is treated with excess HBr. So that means you will expect to see all the CC double bond will be reacted with HBr. So how many organic products will be produced? Now, again, you can make use of a tree diagram. Then you should be able to find out that there would altogether be, let's just use a tree diagram to help us. Okay, so because this one is easier. Okay, let's add the first HBr to the CC double bond on the left. So that will either be the Br here or the Br here, right? Because there are 2 choices. And then we add the other HBr to the double bond here. When you add the HBr to this double bond, it could either be here or here. Similarly for here, it could be this position or this position. So altogether we have 4 outcomes, 4 possibilities. But is there anything that is repeated that is the same? Yes, there are 2 that is actually the same. This one and this one are the same, right? So 1, 2, 3. So how many organic products will be formed? That will be 3 organic products. So the answer is C. Okay. So again, we can make use of a tree diagram. I think this is the most straightforward and easiest way to tackle these kind of questions. Okay. All right. So question 3, the last question for today's lesson. Let's quickly deal with it. Now, it says that compound Z can be made from alkane X or alkene Y. Okay, so alkane X can make this, alkene Y can also use to make this. Okay, so probably by 2 different reactions. So let's focus on the alkane. So alkane X undergoes a chemical reaction to form compound Z. This one. So what is the corresponding alkane? Now, alkane has two reactions, combustion and free radical substitution. So I don't think it is combustion, so it has to be substitution. So what alkane can undergo substitution to form this haloalkane? So it has to be the chlorine atom replaced by the hydrogen atom. So that should be this one. That should be the corresponding alkane, right? Think about with this hydrogen atom substituted by a chlorine atom, it will give rise to this, okay? All right? So what is the name of this? This one would be methyl propane, right? Methyl propane. Okay? Now write a chemical equation for the following, for this reaction. Then, okay, you can put down CH3, CH, CH3, CH3, okay? Reacts with chlorine to form CH3, CCl, CH3, CH3 plus HCl, okay? All right? All right, then we move on to alkene. Alkene undergo a chemical reaction to form compound Z. Again, draw the structure of alkene, Y. So just think about it in another way around. Now we know the product, then we have to figure out the corresponding alkene that forms the chlorine atom. Sorry, from this compound Z. Now think about it, alkene should undergo addition reaction, right? And for addition reaction, we open up the double bond and then we plug in all the atoms or groups of atoms from the reactant, okay? So now, if we think about it reversibly, so that means we need to take away some atom from the product and then forming the CC double bond again. So in this case, probably we will take away a chlorine and also take away one of the hydrogen atom, probably from here. Once we take away the H and the Cl, then it can reform the CC double bond, right? So it turns out to be this one. Okay, do you agree? Okay, so write a chemical equation for this reaction. So again, we can have this one reacts with HCl to form the product. Just copy it from the given structure. Okay, so addition reaction. Okay. Now this reaction also produces another organic product. Draw the structure. So because this one is an asymmetrical alkene, you can also have another product. So this one you have the chlorine atom added to the second carbon. So this time you can have the chlorine atom added to the first carbon. So in this case we can have this one, okay, with the chlorine atom added to the first carbon, okay? So C, an evaluative type question. So which reaction, the one with alkane or the one with alkene, would you prefer? Would you prefer in order to synthesize compound Z? Synthesize means produce. Produce the compound with high yield, high purity, okay? Justify your choice with two reasons. So first of all, we should choose the reaction with alkene Y. Of course, we will go for alkene Y. Okay? And the reason, now whenever you are asked to evaluate a chemical process or chemical reaction, chemical pathway, there are a couple of things you can consider. One, rate of reaction. Is the reaction fast or slow? Of course, the faster, the better, okay? Because you can reduce the reaction time, the experiment time. The second one we will consider is the yield. So which one gives you more product? Of course, the higher the yield, the better it is. The third one, you will think about the safety. So which one is safer? Does anyone involving particularly toxic or hazardous compound? So you may have to think about it. And lastly, you can also talk about the money. But usually in this one, money may not be the major concern. Okay, so we will focus on the rate of reaction, the yield, and also the safety. Okay, now one can also think about from the yield. When you have a lower yield, that usually implies that you have a lot of side product and byproduct. When you have a lot of byproduct, that actually means that you need extra steps, extra work-up process to separate the product, to purify the product. So that would also add into the entire experiment demand. And of course, we try to minimize the steps, minimize the procedures. Okay. So in this case, first of all, we can think about it from the yield, from the product perspective. If you look at the two reactions, you see this one is a substitution reaction. So this one reacts with this one to form our product, but it also gives us HCl. This one is the side product, right? The side product. Okay? However, for the addition reaction, you see we only form one single product and there is no side product. So in terms of the yield, of course, this one has a higher yield. Okay? Much higher yield. Or if later on in Form 6, we will talk about atom economy. This one has 100% atom economy, meaning that all the atoms from the reactants are ending up in the product. Okay? Now, another reason is because, okay, actually the reaction with alkane is a free radical substitution, and if you remember, for free radical substitution, it will produce a lot of side products. So you would say the reaction with alkane will produce a lot of side products, okay, which results in a lot of work-up procedures in order to separate and purify the desired product. Okay, so I try to elaborate a little bit more. Okay, but I think the key is you mentioned about the reaction will produce a lot of side products. Okay, so that would be okay. That would be suffice. Right? You may also talk about from the safety perspective, because for the reaction with alkane, it involves the use of chlorine, which is a toxic gas. So that one, you can also talk about it from the safety perspective. Okay? So that's the idea. So we will stop it here today, and next lesson we will continue with haloalkane. Bye-bye.